Okay, so let's begin. If you haven't downloaded the material for today, please go to Classroom and then download now. 혹시 오늘 그 메테리얼들, 그러니까 그 코드랑 이 수업 자료 받지 않으신 분들은 클래스룸 가서 받아주세요. Right, so today is just simple NumPy practice. If you are already, as I said, if you're already familiar with MATLAB, it'll be super easy for you. And hopefully we can wrap it up within an hour and a half. So NumPy is a MATLAB for Python. It has a very similar syntax. So if you remember your experience with MATLAB, it's basically it's a tool for linear algebra, basically. So there's a lot of easy manipulation tricks for handling matrices and vectors and tensors and even higher order tensors. It's the same deal with NumPy. And when you basically any machine learning, all machine learning, especially deep learning, is all about matrix manipulation. You have to think of your data, your input, as in terms of n-dimensional arrays or n-dimensional tensors, and you have to manipulate it, slice it, concatenate it, reshape it, so on and so forth, while the input passes through your neural network. So you have to be very familiar with all the syntax of NumPy. And actually, we'll be studying PyTorch next week, and the syntax for NumPy and PyTorch are very, very similar as far as matrix manipulation goes. Right, so easily manipulate n-dimensional arrays, right? And NumPy is a foundation of modern deep learning, as I just stated. And neural networks are just a bunch of matrix manipulations. So NumPy, you would be familiar with Probably everybody knows that when you train your neural network, either using PyTorch or TensorFlow, it is done on a GPU or set of GPU cards. So the usual process is that you pre-process your data and you prepare a mini batch, because you're going to do mini batch stochastic gradient descent. So you have to prepare your mini batch every iteration, and that is done on the CPU side usually. So you have to use NumPy to prepare your mini batch, and then you copy that to the GPU. So everything everything for preparing the mini batch is done on the CPU and the actual RAM. And then when you're done, then the mini batch is passed through or copied to the GPU and VRAM. So that is when PyTorch kicks in. Before that, it's all NumPy. And if you are not familiar with the NumPy syntax and APIs, then you can always go to this link and then see what you're missing. Right. And starting today, we'll be using Google Colab. So it's an online Python notebook, as I said this Tuesday. So if you're familiar with Jupyter Notebook, Colab is the same thing. It's a little bit different. The UI is a bit different, and the functionalities are slightly different, but it's more or less almost the same. So you can train your models with Google's GPU and TPU for free for 12 hours. So it's session-based. So it's free for up to 12 hours. If you want to use more than 12 hours, you'll have to pay a very small amount of money. I think it's about, I don't know, like few dozens of dollars per month, I think. 그러니까 이제 한 달에 몇만 원 정도 하면은 꽤 많은 용량을 쓸 수 있거든요. GPU랑 뭐 이런 것들을. 그래서 혹시 12시간 이상을 쓰고 싶으신 분들은 12시간 연속, 그러니까 12시간 이상을 연속으로 사용하고 싶은 분들은 돈을 내고 사용하시면 됩니다. So when I say session-based, it means that if you close your tab on your Chrome browser or your Safari browser, then you'll lose everything. And as I said, you can save your data in here. So you can link your Google Drive, your Google account on your Google Colab so that you can copy things and save things and load things from your Google Drive. So that's a good thing. So when if you think that you'll be needing more than 12 hours to train your model, you can run it for like 11 hours or so, and then save your model's weights in your Google Drive and then reload it after by refreshing your tab, and then go for another 12 hours or so. Right, so please click this link, or if you have already done so, please just keep the browser open. We'll be changing to the Google Colab any minute now. Right. So before we move on to Google Colab, any question? 이제 구글 콜랩으로 이제 실습을 시작할 건데 그 전에 혹시 질문 있으실까요? 네, 그러면은 옮겨봅시다. 네, 구글 콜앱을 처음에 열면은 이제 이런 식으로 뭐 이렇게 탭들이 있을 텐데 여기다가 이제 그 클라스홈에서 받으신 아이파이썬 노트북이 있죠. 이 IPYNB로 끝나는 그 예제 네, 파일을 올려드렸으니까 그거를 여기서 choose 파일 해가지고 다운받으셔서 choose 파일 해가지고 업로드하시면 됩니다. So when you first open Google Colab, going to this link, then you'll be seeing this window. And you go to the upload tab at the last column, and then the file that you've downloaded from Classum, you have to choose that and then upload it. For my stuff, I already did yesterday. So where is it? Where's my? Actually, huh. That's weird. I did upload it yesterday. Interesting. Give me a second. I just need to download it again and then re-upload. Sorry about that. Okay, so when you first open your notebook, you'll be seeing this screen, and go to this connection tab here, so that you can get free CPU or GPU resources from Google. So basically, what you're doing is you're just using a very small amount of Google Cloud's compute resources for free. So you can see that the RAMs and the disks, and actually, I think somewhere here you can, yeah, let's see, somewhere over here. I'm not sure why it's all in Korean. Runtime, right? Here you can go to change runtime type, and you can choose GPU or TPU like this. But today we're just gonna do Numpy, so you don't need them. You just need the CPU. But starting tomorrow and all those practice sessions afterwards, we'll be using GPU mostly. All right, so hopefully everybody's all set to go, right? 다들 이제 요거 여셨죠? 구글 콜랩 여셨죠? 지금 화면 보고 계시죠? 혹시 아직도 문제 있으신 분 있으신가요? All right, so hopefully everybody's good to go. All right, so it's just like Jupyter Notebook. Each cell is you can write any Python code in each cell and then execute each cell to see the outcome. So you just press Shift Enter to load the NumPy library, and then there are some functions. There are a couple of functions that I defined just to make things easier, just to print stuff in a prettier manner. So you go over that. Starting with the very simple concepts: scalars, vectors, and matrices. So everybody knows what scalars and vectors and matrices are. So you just define it like this. This is the NumPy syntax. So an np.array, and then defining a scalar is just simply putting a number, a numeric value here inside the parentheses. And if you want to define a vector, which would be a one-dimensional array, then it will be like this. You put it into a Python list. And if you want to define a matrix, which is a two-dimensional array, then you need to define it in a nested list. It's a list of lists because it's a two-dimensional object. So you define it, and then when you print it, this is what you will get. So A is a scalar, so you just simply see a numeric value. Vector would look like this, and then a matrix looks pretty. If you just print it out, this thing inside the parenthesis, then it will be just a list of lists. But NumPy array recognizes this object as a matrix, so it actually does a matrix. It prints out in a matrix format, so which is easier for our eyes. So, and then there are a couple of properties that you can easily use when you start manipulating the n-dimensional array objects. So here, what you get is dimensionality, the size of the dimensionality. So scalar object has 0 dimension. It doesn't have any dimension. It's a 0 dimension array. So its ndim is 0. B is a vector. So B is a vector. So it's a 1-dimensional object. C is a matrix, so it's a 2-dimensional array, and then so on and so forth. If you define a list of list, or a list of list, so on and so forth, then it'll be a 3-dimensional array, 4-dimensional array. So it'll be like a higher order tensor. Looking at the shape, so this you'll be using a lot. Shape property. So since A is a scalar, there is no shape at all. And then for B, it's a 1-dimensional array with 3 elements. There are 3 elements inside. 1, 2, 3. There are 3 elements inside. So the shape is 3 comma. C is a 2-dimensional array. It's a matrix, and the number of rows and columns are 2 by 3. It's a 2 by 3 matrix, right? So it's right here, 2 by 3. So it's A, and note that this is the outcome, or the value of the shape is a tuple. It's not a list. It's a tuple. It's covered by the parenthesis. So far, so good, right? It's very easy stuff. We go to the n-dimensional array now then. So as I said, if you want to define higher order tensors, it has to be a list of list of lists, or list of list of list of lists, so on and so forth. It's just a nesting. It's just nested lists. So here we're nesting 3. Oh, actually, I just, right. All right. So 3 lists. So there's 1 list here, then there's the 2nd order list here, and then there's the 3rd order list here. So you can assume that this will be a 3-dimensional array. This will be then 4-dimensional array, because there are 4 nestings here. There's 1, 1, 2, 3, 4, right? So you define it. And then when you print it, when you print the actual matrix, the tensors and their dimensionalities, their shapes, what you get is this. So a 3-dimensional tensor would be a list of matrices, right? Because a matrix is a two-dimensional object. So a tensor is a 3D tensor is a 3-dimensional object. So it'll be a list of matrices. So there are 3 dimensions. It's a 3-dimensional object. And the shape is as I said, there are 2 matrices inside. It's a list of matrices, and each matrix has a 2 by 3 shape. There's 2 rows, 3 columns, and then there are 2 matrices. So that's 2 by 2 by 3, right? Simple. If it's a 4-dimensional object, then it'll be 4. Ndim would be 4, and then you can assume you can imagine what the shape would be. So there's, in the very inside, there's a 2-dimensional matrix. So it's 2 by 3, and then there are 2 matrices here, and then the same object is repeated twice. There's here and here. So it's 2 by 2 by 2 by 3. So the shape is 2 by 2 by 2 by 3. So far, very easy. So then what would be the shape of this? It's just a quiz. So what would be the shape of this object here? If you define this as a NumPy n-dimensional array, what would be their shape? You can actually execute this and then just tell me the answer, if you're quick enough. 2 by 3 by 1, exactly. It's a 2 by 3 by 1. So we can actually execute this, as I just said. Why is it my Korean? Right. Let's copy paste this and see what happens. DEF, F equals np.array. This, and then we print object f.shape, right? Oops, something wrong here. Oh, actually, I'm missing a square bracket here. Again. Oh, actually, I have to put in a name. Sorry about that. f.shape. Right. So 2 by 3 by 1, exactly. So this is a rather weird, strange object if you think about it, because inside the very inside the most innermost list, which would be the third order list here inside, it only contains a single object. So it could have been a scalar value rather than a list value of one element. So that is why it has 2 by 3 by 1. So we'll talk about this later, why sometimes we actually need to manipulate or create a matrix that has this kind of weird shape, like when there's a axis or dimension that has the dimensionality of 1, or the shape, actually the shape of 1. Sometimes you need to do it so that you can manipulate, you can like add the matrices together or multiply the matrices together or something like that. So we'll talk about it later. Yep, the answer is 2 by 3 by 1. And okay, so an easier way to define numpy arrays. Sometimes, I mean, you can obviously define numpy arrays like this, but when you go to a higher order matrices, higher order tensors, or if you want to create something very large, with shape of like 100 by 100 or something, then you can't type the elements all the time. So there are easier way to create matrices or define matrices. So there are some couple of examples here. Ones, zeros, full random arrange, and some reshape and S type. So you can imagine what the outcome would be for each cell. The ones is just creating a tensor filled with ones, and since the inner value is 10, you can assume that this would be a 10-dimensional. I'm sorry, a 1-dimensional array filled with 10 ones like this. So there are 10 ones here. And it's a 1-dimensional array. It's a list, basically. It's a vector. For this, you would be creating or defining a matrix, a 2-dimensional array with the shape of 2 by 5. So 2 rows, 5 columns, all filled with zeros, like this. So 2 rows, 5 columns, all filled with zeros. np.full, then you can assume what this would be. This is the same stuff, same thing as the zeros. It's just instead it's filled with 5s instead of zeros. I'm not sure why it's taking so long. All right. Something's wrong with Google Colab. All right, in this case, we can just, reset the whole kernel. So you do this, and then you reset your resources. So unfortunately, we'll have to execute all the cells again. It is weird. It doesn't take this long usually. Huh. Interesting. Oh, I think we are good to go now. We have the resources. Right. So okay, it's working now. So when similar things happen to you, just don't panic. Just reset the kernel, and then you're good to go. We were here, right? So it's time to execute the full. As I said, 2 by 5 matrix, all filled with 5s. Random is it just as it says, it's your 3-dimensional array, 2 by 3 by 4, 3-dimensional array will be filled with random values like this, and the random values will be drawn from a uniform. It looks like a uniform distribution between 0 and 1. So You can actually define it in a bit more in a specific manner. So you can have your random, let's see, let me see here. This is when you can use the link from the slide where I said Numpy stable API somewhere, right? Right. So Numpy documentation, API reference, and then you go to np dot or random. That is what I had, right? Then there was random. So you go to Numpy, searching API here, Numpy random here. And you can set the size. Oh, actually, I guess there is no more parameters you can tune. So all you can do is just set the size, and it'll always be, the numbers will be sampled from always the same range of 1 to 0 to 1 in a uniform distribution. So if you want to use more advanced random functions like normal functions, then I guess you'll have to search for normal, random dot normal. And here it is. So right here. So this is drawing samples from normal distribution, Gaussian distribution. Size you can manipulate, 2 by 3, 2 by 3 by 4, whatever you want. Any n-dimensional array matrix you can define by this function, random.normal. And the location would be your mean value. Scale would probably be a scale, like variance. Right. So here we have random. And then the next one is np.range. So basically, it's just enumerating numbers starting from 0 to the defined value here. So when you define it as a range 10, then you would get a list or a vector filled from 0 to 9, 0, 1, 2, 3, 4, all the way to 9. And if you want to define a matrix or n-dimensional array using a range, then you would have to reshape it. But before that, actually, there's a operator called as type. So you can see that when you define a matrix or when you define an n-dimensional array using a range, then you would get a integer value. But if you want to manipulate when you want to convert it into a float value, then all you need to do is just put as type float operators. When you do this, then your matrix would be, your vector would be filled with float values like this. You can see the decimal points here. And as I said, if you want to define a n-dimensional array, then all you need to do is just use the operator reshape. So your values 0 to 9 will be, will be reshaped to a 5 by 2 matrix, 5 by 2. So you can imagine what would happen if your shape doesn't match what you've created. 5 times 2 is 10, so this is why that it works. But if you put 3 here, then it wouldn't go, because you cannot, or as it says, cannot reshape array of size 10 into shape 5 by 3, because that would require 15 elements, right? So you'll have to pay attention, right? Now the quiz. So create a 4 by 3 by 2 tensor filled with numbers starting with 0.0 all the way to 23.0. Can you do it? That was fast. NP arrange 24 as type float reshape 4 by 3. Yep, that would be the correct answer. Let's try if that works. See if that works. B. Exactly. 0 all the way to 23.0. So you have to always pay attention to the specs. So it's a float value. So it's correct float value all the way to 23, shape 4 by 3 by 2. So inner matrix would be 3 by 2, and there are 4 repetition of the same matrix, 1, 2, 3, 4. So it's 4 by 3 by 2. Good work. Right, moving on to indexing and slicing. So let's collapse so we can expand it. So there are a lot of things here. It's just, different ways to access elements inside a vector or matrix or tensor. And slicing means that, taking a subset of it. So we can actually see, we can comment everything out and see what happens for each one. Right. So what you do is you just define a index 0 to 9, and then what you're doing is you're accessing the first element, and then we'll just see what happens if you start accessing other elements. The first element is obviously 0. The second element is obviously 1, but then you can do things like -1, -3. So -1 is the last element. -3 would be the second and the third element from the last. So it will be 9, 8, 7. So that is why you get 7 here. So you have to, there will be a lot of times opportunities for you to use negative in this index values when you manipulate matrices in Numpy or PyTorch. So keep that in mind. And moving on to slicing, see what happens. So when you have a vector like this, if you define your index value like in this index value like this, like a range is starting from 0 to 10, that means that you want everything, because your shape, the vector shape is 10, right? It's a 10-dimensional, it's a one-dimensional vector with 10 elements. So if you get everything, then you get the entire thing again. If you do this, you can actually skip the end position. So this will be the start position, this will be the end position. So you can actually skip the end position. It'll always just assume that you're taking everything. So the same value as this here. Same value as here. You can actually skip the start index or start position as well. Then it'll automatically assume that it'll be 0. So again, same thing. You can actually skip everything. So if you skip everything, if you just skip everything, then the PyTorch, the Numpy Numpy interpreter will recognize this as 0 to 10. So again, like this. So keep that in mind. So having a column would be basically, having a column is just basically saying that I want elements from start position here to the end position here, not included. So start position included, end position not included. Right. So we'll be moving on again. So then you can see what would happen if you start manipulating, like taking slicing like this, like 7, 5, 2, 5. You can imagine what would happen. So 7 colon nothing is that you want to take everything, all the elements, starting from the position 7 all the way to the end. And 7 is exactly here. So it would be 7, 8, 9. You are taking 7 to the end. So it's 7, 8, 9. This would be starting from 0. So assuming that you're starting from 0, the first element, you want to take everything up to 5, excluding 5. So it will be 0, 1, 2, 3, 4. You can go both ways. So 2 and 5. So you want to start from 2 and end at 5, excluding 5. So you would get 2, 3, 4. So this would be, indexing and slicing. Good, right? So quiz, what would be a -4 colon nothing? Or how about nothing colon -8? You can execute this in your cell. Actually, we can do this now. Let's get this in. Print object A, -4, nothing. See what happens. 6, 7, 8, 9. All right, yeah, I'm always forgetting the A, -4. The correct answer is 6, 7, 8, 9. Because you're starting from the fourth element from the end. So fourth element from the end is 9, 8, 7, 6. You're starting from the fourth element from the end. So that's what that would be 6. And then you go all the way up to the end. So it's 6, 7, 8, 9. And the second one is, I guess people already have executed that. 0, 1. Let's see if that would work. -8. -8. Now, obviously, this is starting from the first position and going all the way up to the 8th position from the back, excluding that 8th position. So if you go, so it's 1, 2, 3, 4, 5, 6, 7, 8, and you want to exclude it, so it will be just 0, 1, and that's what you get. All right, all good. I think people are following very well. And these are, so we introduce a new element here. So the first two are start and end position. Then there's the third element here, and let's see what happens. So if you put 2 here, that means that you want to skip every other element. So that is why you get 0, 2, 4, 6, 8. So you start from the 0 all the way up to the 10, excluding the 10th. Well, there is no 10th. It'll be, so it's starting from the beginning to the end, while skipping every other element, 2. So you get 0, 2, 3, 0, 2, 4, 6, 8. You can imagine what would happen with 3. So you're skipping 2 elements at a time. So it's 0, 3, 6, 9. And the final one is starting from 2, going all the way up to 6, excluding the 6th element, skipping 2 elements at a time. So that would be, you start from the second. So 2 to the 6th. So 2, 3, 4, 5, 6, but you are excluding 6. So you're left with 2, 3, 4, 5. And then you're skipping 2 elements at a time. So 2, skipping 3, 4, 5. That is why you get 2, 5. Good. Hopefully this is good. So when you want to, so this would be especially useful when you want to take only the odd elements or the even elements or whatever elements from your output or from your input, wherever, basically, again, another way to cleverly manipulate matrices. Right. And the final one is, so this is nothing, -1. This would be interesting. So this is, instead of skipping 1 element or 2 elements, you're actually doing something new. And you can imagine what would happen. Let's see what happens. So -1 means you're actually going backwards. So when you have a matrix, when you have a vector and you want to reverse that, then you can simply just do this. So start position, end position, all just, blank. So it's just starting from the beginning to the end. And then -1 means not skipping, but actually going backwards. So negative is actually going backwards, right? And then you can imagine what would happen with this. So you start with the 8th element and then going back all the way to 5th element, going back. So that is why you get 8, 7, 6. So 8th element. And then, so actually, sorry, you have 0, 1, 2, 3, 4, 5, all the way to 8th element. So you're starting with 8, and then you're ending at 5, going backwards. So that is why actually excluding the 5, because this is a end position. So excluding the 5. So you would be left with 8, 7, 6. So that is why you have 8, 7, 6 here. 8, 5. What would happen then? Actually, if you do 8, 5, then it will be just a blank list, because this is doesn't understand. You start, so without the -1 here, you're actually going in an ascending manner. And when you go ascending manner, you can't start from 8 and end at 5. So that is why you're left with nothing. So if you want to do something like this, then you'll always have to have -1 here. Good. So final quiz, create 963 using the predefined list or vector here. So can you pick 963? 2 different answers. Actually, yeah, there's not just one answer here. There are a lot of different ways to define 963 out of A. We'll just take the first 2 answers from 임세종님. Print object. Oops, sorry. Not sure why it's not being copy pasted. All right. Answer 1. 963, that is correct. So what you did is we start with the 9th element, which would be here, and then we go all the way to 2, but skipping 3 elements at a time. So 1, 2, 3, we skip. Actually, sorry. we skip 2 elements at a time. So it's skipping 7, 8, you get 6. Skipping 4, 5, you get 3. So that is why you get 963. Another answer was actually starting with, it's a slightly larger range. Pen 1, answer 2. See if that works. Actually works again. Because whether you start from 9 or 10 doesn't really matter, because you're just starting from the final element anyway, and then you're going all the way back to either 1 or 2. Doesn't matter, because you're actually skipping 2 elements at a time. So you'll be landing at 3 no matter what, right? Right. Yeah, there are different. Yeah, as Wang Yusung said, there are different ways to define the same element. I mean, same matrix. Actually, same vector. Sorry about that. It's always very confusing. Right. So moving on. So that was all indexing a single element, a one-dimensional array, which is vector. And you can do the same thing with matrix and tensors. So here it's just differently, just some examples. We'll go into the details. We got a lot of things to cover anyway. So we'll just execute this and see what happens. So what you have is a square matrix filled with elements 0 to 8, all integers. And then what you're doing is you're accessing element in a C++ style or in a Python style. Not sure what MATLAB does, how MATLAB goes, but it's the same thing. So if you whether you do a C++ style or when you go or regardless whether you do Python style, it's the same thing. You're accessing the first row, first column, first row, first column. First row, first column. So that would be 0, right? And then if you access the second row, second column, then second row, second column, that would be 4. So, all good. Right. I think we have actually. Oh, so slicing. Okay, so we can't skip the slicing part actually. So we'll just comment this out. How to access the last row, the second column, and how to create these. So these are important. Actually, are there already takers? There are already takers. So how to access the last row? Not sure. 김희영님의 정답이 몇 번째 퀴즈에 대한 정답인지 모르겠네요. We can actually. I'm not sure what. So a lot of answers are A-1. See if that works. So yeah, see if that works. Print object, A-1. Answer, let's see what goes. Right, that is the last row. So actually what you're doing is, the first index is the row index. The second index is the column index. What you're doing is you're skipping the column index. You're skipping the column. Let's see if this also works as well. So see, when you skip the column index, it means that you're just taking all columns, right? It's the same deal with the starting and ending. When you skip the start and end, it just assumes that you're taking everything. Here, you're skipping the column position, the column index, and it means, so it is the NumPy is assuming that you're taking all columns anyway. So you're just specifying the row index, which would be the last row. So that is why you get the last row here. If you want the second row, then you get the second row here. How to access the second column? I actually gave you guys the answers away. So second column is there are a couple of incorrect answers. So if you did 2, comma like this, then what you get is actually it's pretty confusing. What you get is, oh, I guess that was another answer for taking the last row. All right. So yeah, again, there are different ways to arrive at the same answer. So -1 or 2 is the same thing. -1 is 2 because it's the last row anyway. And the second row, accessing the second column, you would have second column here like this. Then you would get, oh, sorry. What am I missing here? Oh, second column 147. I guess you can't just simply ignore the row column. That's something I forgot. So So when you access the second column, it means that you want to take all the rows, right? So second column is 1, 4, 7, and that means that you're taking first row, second row, third row. So you're taking all rows. So that is why you need to have column in the row position, the row index. So the left side of the comma is the row position. The right side of the comma is the column position. And when you want to take entire column, then you have to, when you want to take the entire row, then I guess you can't just leave this as a blank, but if you have to actually, explicitly put a column there. You're actually still ignoring or still skipping the start position and the end position, because it would have to be 3 here, because there are 3 rows. So first row, second row, third row. So you have to put 0, 3, 0, colon 3 to be really explicit. So you're taking all rows and you're taking the second column, 1, 0, 1, 2. So you're taking the second column, but you can actually ignore this like this, or you can just go like this. It's all same deal. It's the same thing, right? And the last quiz is how to create 8-5 using A. 8-5 already there are different answers. So 8-5 is what? 8-5 is this. So you want to go backwards. So you can actually take the, let's see, second row, third row, last column. So how would you go if you wanted to take second row, third row? So you want to take the second row, third row, and only the last column. So last column is -1. So let's see what goes. It's 5, 8, right? But you want to do it you want to reverse that, and reversing that would be -1, right? Right. What was that? Is that correct? Actually, you can skip this. Oh, sorry. Yeah, you can, because you have up till here, you have a one-dimensional vector, and then you would have to reverse that. So you put colon -1 and see what goes, and then you get 8-5. But there were different answers actually. We'll take one from Kim Hyung-nim. See if that gives you the same answer. Okay, the copy pasting doesn't really work well. I guess that doesn't work. It's a weird syntax, actually. Oh, okay. Oh, sorry. It was mistake on my part. So, okay, that does work. So let's see what happened here. Let's see. So you take the first row. No, I'm sorry. So this is the row position, and this is the column position. So what happens here is that you take, you go reverse in the row selection, and starting with nothing, and you end with the -3, which would be the first row actually. So excluding the first row. So this would give you 2 rows in the reverse. This would give you 2 rows in reverse order, and then you take the last column, which is this is the last column. So that's why you get 8-5. Okay, that's good. Pretty convoluted though. All right. So okay, so hopefully everybody is following along. And then the same deal with tensors. So matrix manipulation, indexing and slicing, all that. If you know how to do it on the matrix, on matrices, you know how to do it on tensors. So we'll just skip this part. So 432, reshape 432, then you have a 4x3x2 tensor, and then accessing a specific element, you would need to have 3 positions: the first position, the second position, the third position. So you are accessing the second element. Is it the second? No. I'm sorry. So there's 1, 2, 3, 4 elements, four elements, and you're accessing the 2 here, and within the 2 you're accessing the row here, and then you're accessing the first column. So that would be 14. That is 14. And you can solve the quiz on your own time. We have to actually move on. So yeah. I mean, instead of having, so it's the same deal. You can remember all the column manipulation, which would be the slicing, and then you can reuse the things we've done with things we did in the matrix manipulation with the column with commas. So the comma here. So the commas separate different axes. 이제 그 차원을 분리하는 게 컴마고 이제 컬러는 그 차원 내에서의 이제 시작과 끝을 의미하는 거니까 이제 그것들 잘 조합하시면은 이제 뭐 텐서든 뭐 4디멘션이든 5디멘션이든 쭉쭉쭉쭉 할 수가 있습니다. Alright, so then there's a trick. Sometimes I don't use this very often, but sometimes it's very helpful to use a conditional indexing. So here what you have is a matrix, a rectangular matrix 3 by 2, and then what you're doing is you define your index like this. So a modular 2 equals 0. So actually before we print out, it is printing out the index. So here what we're doing is we're printing out the index, which would be true, false, true, false, true, false. So what you're doing is you're using the predefined a, and then you're doing modulo operation with 2, and you want to see if it's even. Basically it's just finding the even numbers within the matrix. And obviously the first column is 0, 2, 4. So these are the even values, and the second column is the odd values. So this is true, 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 false, 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 and see what happens when you actually print a index a id x and just test. Then you get 0, 2, 4. So actually what you're doing is you're preparing an index that you will be using to access the values inside your n-dimensional array. So you have the index, which is already a 2 by 3, 3 by 2 matrix, and then you simply put that into the square bracket, and then you'll be able to extract the things that you're interested in, which are 0, 2, and 4. All good, right? So you can do modular 2, modular 3, whatever you want. And here what we're doing is 3, 4, 5. So you can imagine what you need to do. 3, 4, 5. 3, 4, 5 are the values that are larger than 2, right? So you would have to define your index to be larger than 2 using a. So you would have to use a inequivalent, the bracket. 그 꺽쇠를 영어로 뭐라 하는지 까먹었네. I forgot how to what these are called in English. Are they still brackets? Anyway, you can use them. So basically inequality operator, and then define your index to be larger than 2, then you'll be able to access 3, 4, 5 using that index. Right. And actually, I guess we can actually just try it out. Index a larger than 2. See what happens. Larger than 2, so obviously all the values 3, 4, 5 larger than 2 are true, and then you'll be able to extract 3, 4, 5 out of it. So that is how you do it, basically. Right. So there are a lot of different ways to define a conditional index. So you can use your imagination. Right, taking specific elements from a vector. So well, I guess you can, based on this experience here, you can imagine what would happen. Taking 0, 2, 3 out of 10 elements in ascending order, then you would actually get 0, 2, 3. That is it. Very simple. Moving on to the specific elements from tensor is again the same deal. Now, when you define a matrix of 6 rows and 4 columns, 6 by 4 matrix, and then you're taking all rows, but only what columns? The first column, the third column, and the fourth column. So first column, the first column, the third column, and the fourth column. So you would get this here. On the other hand, if you take first row, third row, fourth row, all columns, then you would get the output like this. So the first row, third row, fourth row. So it's 0, 8, 12. So 0, 8, 12, right? And all columns. You've got all columns here. Right. All good. Right, then the math operations. So this is a bit more intuitive. So when you have two objects, when you have two NumPy objects, vectors, scalars, matrices, tensors, you can just do whatever you want. As long as their shapes match, the two objects, as long as their shapes match, you can multiply them, you can add them, you can subtract them, you can divide them, whatever you want. So it's just a couple of examples. So we have 3x2 matrix filled with 0 to 5 and 1s. So this is defined by 1s here, defined by 1s. And then what you do is you add them, subtract them, you multiply them, you divide them, and you get these. And their shapes match. Both A and B are 3x2 matrices, right? So there's no problem. Unary operations. Sometimes you can just do unary operations, and these are some examples, like taking sum, summing out the entire matrix, or taking an average value, taking a max value, taking a min value. These are all unary operations. You can do it with one matrix, and let's see what happens. You have a 3x2 matrix, 0, 1, 2, 3, 4, 5, and then you're taking the sum. So if you simply just put a dot sum, then you're just adding all the things inside your object. So if you just add 0 all the way to 5, you get 15. But you can actually specify to which axis you want to sum up. So if you sum with respect to the first axis or the second axis, you get different results, and you would retain the dimensionality to some extent. So here we are adding with respect to, we're summing up with respect to the first axis, which means that first axis means with respect to the row, So if you add row-wise, then you get 6 here, and you get 9 here. That is why you get 6 and 9, and you are left with a one-dimensional array. If you just simply do a sum with nothing inside the parentheses, then you're left with a scalar value, because you're collapsing all the dimension, all the axes, all the dimensions. But if you specify a certain specific column, if you specify a specific axis, then you're still left with a one-dimensional array. Same deal with this. So you're summing with respect to the column. So it's a column-wise addition. So you have 1, 5, and 9. You're adding by the columns, first column, second columns. You add these two columns, you get 1. These two columns, you get 5. These two columns, you get 9. So that is why you get 1, 5, 9. All right. So far so good, right? If you take the average, then this again, there's nothing inside the parentheses, so you're collapsing all the dimensionalities, and you're left with a scalar value of 2.5. Max and min, all the same thing, right? So if you had put axis here 0, then you would get a different result. Obviously, you will get 2 and 3. So which means that you averaged along the first axis, it was a row-wise averaging. So what you get is average of 0 to 4 is 6 divided by 3 is 2. 1, 3, 5, if you add them up, it's 9 divided by 3 is 3. So that is why you get 2 and 3. Okay, good, right? And there's a quiz. So given a three-dimensional tensor, what is the mean of the sum with respect to the last dimension? We have about 30 minutes. I think we can try it out. So try it out on your own, see what happens. What is the mean is basically average, right? So when you average with respect to the last dimension, last axis, what happens? Answer 46. So let's see if that is correct. Print object a dot. I'm just going to copy paste this. A dot mean with respect to the last axis -1. Let's see if -1 works actually, even here. Oh yeah, I'm always forgetting the name. Answer. And not sure why people got 46. Let me print out the object. Okay. So we have a tensor that looks like this. So it's 2 by 3 by 4 three-dimensional array, and you want to mean. Oh, sorry. I'm sorry. It's a mean of the sum. Sorry, mean of the sum with respect to the last dimension. So that is My fault. Mean of the sum. You have to first sum it up to the last axis and then take an average. So that is 46. That is correct. Yep. Oh, we can actually see what happens procedurally. So you take the sum with respect to last axis, which would be 0, 2, 3, 4. So it's well, there's no longer row and column. But anyway, so if you sum it up with respect to the last column, then you're left with a 2x3 matrix, because you're collapsing the last column, right? You have a 2, 3, 4, 2x3x4 tensor, and if you collapse the last axis, then you are left with 2x3 matrix, right? So that is why you're left with 2x3 here, and then you would take the average, you sum everything up, and then divide by 6, you get 46.0. Good. Comment from Kellenbach. It says to take the sum. Yeah, that was my mistake. Take the sum with respect to the last dimension first, right? Yep, you're correct. And the dot products. So dot products is again, it's a pretty easy concept. If you have two vectors, taking an inner product would be easy. You just use dot operator here, and that's it. So 0, 1, 2, 1, 1, 1. Then dot product between the two would give you 3. This multiplication of these two, 0, 1, 2, add them all up, you are left with 3. So that's good. Matrix multiplication is a bit different. So if you have two matrices where the shapes have to match, that supports the matrix operation, matrix multiplication. So the first element should be 3 by 2. If you have a 3 by 2 matrix and you want to multiply to another matrix, and the second element has to start with 2 rows, because it has 2 columns. So 3 by 2, 2 by 3. When you do a matrix multiplication, then you're left with, but you can use NP dot, or you can use another operator, which is a bit more easier to type, which is et operator. So both give you the same results. NP dot AB and A et B give you the same result. It's just 3 by 3 matrix. This is 3 by 2. This is 2 by 3. Multiply them together, then you are left with 3 by 3 outcome. And so far so good, right? You can use either NP dot or A et B. It's the same deal. If you go to the tensor, so 3-dimensional or higher, things are a bit different between NP dot and A et B. So this is a good example. If you have a 4 by 3 by 2 tensor, and if you have a 4 by 2 by 3 tensor, so 4 by 3 by 2, 4 by 2 by 3, and then you want to multiply them, then what would you do? So typically in deep learning, when you do mini batch stochastic gradient descent, the first axis is the batch axis. So when you have a 4 by 3 by 2, it means that you have 4 elements in your mini batch. We'll talk about the mini batch gradient descent tomorrow. No, not tomorrow. Next Tuesday. So if you're not familiar with stochastic gradient descent, just please just follow along. Be patient. Anyway, so as I was saying, in typical deep learning, the first axis is the batch axis, and then the remaining axes are your actual input, your sample dimensions, the dimensions that corresponds to your samples. It could be like an image of 3 by 2 resolution, or it could be like a multivariate time series with 3 temporal time steps with 2 channels, something like that, basically. So when you have things like that, in those situations, when you do matrix multiplication, what you want to do is usually you want to repeat the same matrix multiplications along the batch axis. So there are 4 elements here, 3 by 2, and then there's 4 elements of 2 by 3 matrices. And what you want to do is you want to multiply these 3 by 2 and 2 by 3 matrices 4 times along your batch axis. That is the usual situation. So in those cases, in those scenarios, what you need to do is you need to use A et B. So what happens here is that you can ignore just the elements here. What happens with A et B is you are left with 4 by 3 by 3. So as I said, if you wanted to do 3 by 2, 2 by 3, so if you want to multiply 3 by 2 matrix inside the batch and 2 by 3 matrix inside the batch, then you are left with a 3 by 3 matrix inside the batch, which would be 4 by 3 by 3. And that is what A at B gives you. It's a 4 by 3 by 3 matrix. 이 중요하니까 한국말을 한번 다시 하면은 지금 이게 4 by 3 by 2이고 4 by 3 by 2고 이제 4 by 2 by 3인데 그 텐서가 이제 두 개가 있잖아요. A and B가. 근데 그 두 개를 뭐 행렬 곱을 하는 방법이 두 개가 있는데 이제 주로 우리가 딥러닝에서 하고 싶은 거는 앞에 거가 이제 배치라고 생각을 하고 뒤에 것들을 가지고 곱을 하고 싶단 말이에요. 이제 3by 2랑 이제 2by 3을 곱을 하면 3by 3이 나오니까 3by 3짜리 곱이 아니 3by 3짜리 행렬이 4개가 나오기를, 왜냐면 4개의 배치가 있으니까 4개가 나오기를 원한다고요, 주로. 그럴 때 이제 A at B, 그러니까 이 at 오퍼레이터를 사용해야지 4by 3이 3by 3이 나온다. 만약에 이거를 np.을 사용하면은 so back to English. If you use np.dot instead, then you're left with something a bit weird, bit hard to understand. You're left with 4 by 3 by 4 by 3 4-dimensional tensor. So this is a bit weird because you started with 3-dimensional tensor, and then when you do np.dot, you're left with 4-dimensional tensor. So you actually increase your dimensionality by 1. Basically, what happened is that you collapse these 2 and 2. So 2 and 2, these are the same elements, 2 and 2. And that is why you're left with 4 by 3 by 4 by 3. So that is why you're left with 4 by 3 by 4 by 3. So typically, you wouldn't need to use np.dot in the higher order tensors. You would use at instead. But there could be some corner cases where you have to use np.dot. I'm not sure. I've never run into that kind of situation, but sometimes you might. So when you do that, you have to be really, really careful about your endims and your shapes so that they at least have some matching, elements. And then you have to think about what kind of outcome you would get. In this case, you get 4 by 3 by 4 by 3. So read their definition, np.dot, very carefully. In here, you can just search for np.dot. Actually, what np.dot is a wrong. Yeah, so here you can carefully read what happens here when you use multidimensional dot product. All right, moving on. Shape manipulation. So we're almost going towards the end. Shape manipulation. So when you, actually we use the reshape operator very heavily up till now. So you probably are already familiar with the reshape operator. When you define your vector and then reshape it into 2 by 3 by 4, you would get a 2 by 3 by 4 matrix. But then again, you can reshape that into any other form you want, any other shape you want. So this is like this. So you start with 2 by 3 by 4 tensor, and then when you collapse the first 2 axes, 2 by 3, you just simply put 6 instead, then you would get a 6 by 4 matrix. And you can do, you can actually, similar to the skipping the beginning index and the end index in the slicing tutorials, you can actually skip the remaining x's with -1. So if you put it like this, like 6 -1, you would get the same results. Because you are given, so here the A May tensor has a shape of 2 by 3 by 4, and when you reshape it into 6 by something, that something has to be a 4 in order to make it work, right? 그러니까 이제 이게 -1이어도 무조건 4가 될 수밖에 없다는 거죠. 그렇기 때문에 이제 numpy가 이거 -1로 써도 알아서 그냥 4로 이제 또 스마트하게 똑똑하게 인식을 하고 6 by 4로 이제 잘 변형을 해준다, 그런 겁니다. Right. So you can do it in a slightly different format. So let's see, 3 by 2 by -1. See if that works. Still works, right? 2 by 3 by -1. You get, so you started with 2 by 3 by 4, and you're left with 3 by 2 by 3 by 3 by 2 by 4 instead. So it's working pretty well, right? So what would happen if you do like this? So you already have all the things you want, You have 6 by 4, which is already 24. You have 24 elements inside your A object. So 6 by 4 is already enough to, define a new reshaped object, right? But you're putting a -1 at the end. So what would happen then? we can actually see what happens. Right. What happens is this. So you have a 6-byte. Let's see. Let's actually type the shape of this as well. Right. So its shape is 6 by 4 by 1 because you are using -1, which is actually which is unnecessary because, as I said, you have already all the space you need, all the dimensionalities you need to fit your A object within, but then you're putting one more like additional unnecessary axis or unnecessary dimension. So that is why it has to be a 1. So inside, these are just one-dimensional lists or one-dimensional arrays that only contains one element at a time. So it's like, as I said, sometimes you need to do this. So like 6 by 4 by 1, but this basically you're actually wasting a one additional axis by doing so. Right. So this is exactly that, adding an extra dimension. So sometimes you have to add additional dimension because sometimes you want to do like, binary math operations like this, binary math operation like this. And in order to do so, the two elements, A and B, must have the same matching dimensionality, same matching shape, or at least the same endim at least. So in order to do so, sometimes you need to add more dimensionalities to your predefined object. So this is what's happening here. If you have 1, 2, 0, 1, 2, it's just one-dimensional array. You put none here, and then you will get one additional thing. So this is exactly the same thing as reshape by 3 by -1, and then reshape. It's exactly the same thing, right? So reshaping and using none is the same thing. But if you don't want to use reshape operator all the time, so what you do is you just put one additional. So you can see the comma here. So before the comma is the row, after the comma is column, but doesn't really make sense because A is a vector, so there is no row or column. It's just one thing there. So putting a comma and then putting none after that indicates that you want one additional axis put to A. So that is why you get 3 by 1 matrix now. So non-operator is a good shortcut to use instead of using reshape. All right, so hopefully everything is pretty clear. One additional quiz here: how to change a 3 by 4 matrix into 3 by 1 by 1 by 4 4-dimensional array using none or reshape. Is up to you. Using reshape, you would need to reshape this into 3 by -1 by -1 by 4. Using none, you would have to use a square bracket, colon, comma, none, comma, none, comma, colon, right? Actually, let's see if that works. NP1's 3 by 4, and then you want to put comma, none, comma, none, comma, and then you want to see its shape, right? It is 3 by 1 by 1 by 4, and its values look like this. So a lot of ways to dimensionality: 3 by 1 by 1 by 4. All right, so far so good, right? And some more manipulation, concatenation. So when you have two matrices or two n-dimensional arrays, you can put them together. You can paste them. You can put them side by side. You can stack them horizontally, vertically. So these V stack and H stack are the examples. Stacking vertically, so you have two matrices, A and B, all ones and all zeros, right? 3 by 2, 3 by 2. And then if you stack them vertically, you would get this. If you stack them horizontally, you would get this. And you can actually repeat the horizontal stacks, like H stack, ABA, then you would get ones, zeros, ones. And you can do the same thing with V stacks as many times as you want. V stack, H stack, as many times as you want. But I recommend that you use concatenate operator instead, which is easier to generalize to higher order tensors. Like V stack and H stack, they're intuitively easy to understand when you're dealing with matrices, but when you're dealing with 3-dimensional or 4-dimensional or anything higher, then concatenate is actually easier to, easier to understand and manipulate. For example, here, concatenating these 2-dimensional matrices along the first axis, that is the same thing as V stack. So basically the first axis is the row axis, right? So you want to concatenate these two objects in a row-wise manner. And here, if axis is 1, then you want to concatenate them in a column-wise manner. So you would get this, like the H stack. And if you were dealing with 3-dimensional tensors, then you could use axis 1, axis 0, 1, all the way up to 2. So this is the quiz. You can solve it on your own time. Actually, we're running out of time, so we have to skip some quizzes here. Right. So, question from Mindoki. Is there any difference with stack and concat respect to memory? Very good question. And the answer is, I don't honestly know. It's a very good question. You can actually look it up here, H stack. And this is not good enough. Well, if you're interested, you can actually read their source code, because Numpy is an open source project. So you can read all their source codes if you want, if you're interested in the kind of stuff. Never knew that, but inside they are using concatenate. So it's the same thing. It's just a shortcut. So new discovery, I never knew. So I guess VStack also uses concatenate inside their source code. Interesting. Matrix transpose, you can just use a transpose object here, a transpose operator here. It's a unary operator. If you have a two-dimensional matrix, you can use the capital letter T, and then you get a transpose. But if you go a higher order, like transpose is a two-dimensional concept, but if you want to somehow transpose 3-dimensional or 4-dimensional tensors, you can use transpose like this in a more like a generalized manner. So if you have a 3-dimensional tensor, 4 by 3 by 2, and you want to reshape their first axis or second axis or third axis, you can use this instead. So transpose operator, and then so it's np.transpose. You want to transpose the object A, and what you do here is what you are doing is you're swapping the second and the third axes. So that is why it's 0 to 1. So originally it was 4 by 3 by 2, but when you swap these two, this and this axes, then you would get 4 by 2 by 3, 4 by 2 by 3. And when you go like this, like 1, 0, 2, what you're doing is you want the first axis go to the second place, the second axis to go to the first place, and you're leaving the last axis as is. So you would get what you get. You would get 3 by 4 by 2. You will get 3 by 4 by 2, right? So when you want to transpose, a higher order n-dimensional arrays, then you will need to use transpose operator. Right, so we're almost coming to the end. So broadcasting is a very important concept because sometimes when you want to manipulate your matrices, when you want to do math operations between your two matrices that don't exactly have the same shape, sometimes it just works automatically because PyTorch or NumPy understands what needs to be done to match the shape between the two objects, and it's called broadcasting. So here you have one object that is a vector, 1 to 3, and another object which is a scalar, right? So adding the two shouldn't work because their shapes don't match. This is a 1-dimensional array, and this is 0-dimensional scalar. But somehow it does work because when you add, so here 0, 1, 2, and then A plus B, outcome is 2, 3, 4. So it does mean that B was added to each element at a time. So 2 was added here, 2 was added here, 2 was added here. So that is why you get 2, 3, 4. So it's a pretty smart move on the NumPy side. So when you have even though B doesn't match the dimensionality of A, it just it just increase the dimensionality and copy paste the same element all over. So basically what you are left with. So here inside this plus operation, B was treated as a 2, 2, 2. So basically treated as a one-dimensional array filled with twos. So that is why you get 2, 3, 4. Same deal with A minus 4, A minus B, A times B, A divided by A divided by B. It all works. It all works. So that is called broadcasting, when the shape is automatically matched so that the math operations can be done, can be executed. And typically how it's executed is that you increase the dimensionality and copy paste the same element all over. I mean, well, you don't do it. The PyTorch and NumPy does it for you. See what happens here. So you have two elements, A and B. A is a two-dimensional matrix. B is a one-dimensional array, one-dimensional vector. And you are adding the two. And see, there's no an error message anywhere. So what happened is that you can see 1 and 2, 1, 2 was added to the first row, the second row, and the third row. So that is why you get 1, 3, 3 by 5, 7. So again, 2 by 1, one-dimensional B vector was expanded. It was basically expanded to the two-dimensional matrix filled with 1, 2, 1, 2, 1, 2, like 1, 2, 1, 2, 1, 2. So internally, it's treated as a two-dimensional array, two-dimensional matrix, and then it is this plus execution was done internally. Right. So quiz. Well, I mean, we don't have a lot of time to do the quiz, but this is a pretty important concept. So what would happen if B were like this? So if B, let's redefine B as this. Redefine B as this. Missing a parenthesis. See what happens. So B is 2 by 1. So we're actually wasting an additional axis by using 1 here. So it looks like this, right? So B is a 2 by 1. And interestingly, it doesn't work here. See, when it was just simply when it was simply a one-dimensional matrix with shape of 2, so when B was a vector, A plus B did work. But now that we've explicitly defined B to be a 2 by 1 matrix, now it doesn't work. And the reason is, can you guess? 이게 안 되는 거를 이제 미리 상상하실 수 있으셨으면 아주 좋은데, 그러니까 이제 아까는 그냥 B가 벡터였을 때는 아무 문제 없이 됐잖아요. 근데 이걸 이제 우리가 2by 1짜리 매트릭스로 하고 나니까 지금 에러가 나죠. 이제 안 맞는다 이거죠. 지금 안 맞는다. 그러니까 지금 보면은 broadcasting이 안 되는데, so you can see the error message here. Operands could not be broadcast together because the first element being A, has a shape of 3 by 2. Second element has a shape of 2 by 1. So that is problematic. When it was just 2, meaning that it was a vector, then this 2, I'm just gonna let me make it explicit. So I'm gonna call this C. I'm gonna call this B. Call this C, and then I'm gonna print out their shape, and then A shape, and then let's see. So A and B have at least one matching axis, which is 2. So 2 and 2 matches. So all the NumPy needs to do is repeat this 2 3 times to match the entire shape. But when it's actually, this is C, I'm sorry. But when your matrix, when you have a second element that looks like this, then there is a matching shape. There is a matching axis, but the C is already two-dimensional object, so it cannot be expanded in any manner. There is nothing to expand. When B was a one-dimensional vector and A was two-dimensional matrix, B could be expanded to be a matrix, but C is already a matrix, so it cannot be expanded anymore. So that is why the broadcasting doesn't work. 이해가 되셨죠? 지금 브로드캐스팅 안 되는 이유를. 네. 그럼 요건 어떻게 했느냐? 요거는 이제 답은 요건 되겠죠? 이거 이제 1 by 2니까 이제 1 by 2니까 이게 만약에 1 by 2였으면, if it was 1 by 2 instead, there shouldn't be a problem because 2 matches here, 2 matches. So maybe my description was not entirely exact. So when you already have a matrix of when you already have a 2-dimensional matrix, so A matrix, C matrix, and if their shapes, if their dimensionality, if their certain dimensions match exactly like this, their columns match, right? The columns 2 match, then all the NumPy needs to do is copy paste this 2, basically expand this into 3, 1, 2, 3, and that's not a problem. The only problem is when it doesn't match exactly. So I'm going to have to define another D here. So D has 2 by 1, B, A by A plus C, A plus D, A plus C, A plus D. So here, A plus C works with the proper broadcasting. A plus D doesn't work because they no longer have a matching axis. So that is why the broadcasting cannot work. 이제 아주 중요한 컨셉이니까 잘 이해를 하시고 넘어가시면 좋을 것 같습니다. 그러니까 여기도 이제 되겠죠. 여기도. So the same principle can be applied here. A is a 2 by 3 by 2 tensor. B is a 3 by 2 matrix. So there is a matching axis here. 3 by 2 matches these 3 by 2, right? So all the NumPy needs to do is repeat this 2 times, so there can be 2 sets of 3 by 2s inside, and then you can just simply add them together, right? So it works. And yeah, you can use none to actually expand. You can expand B explicitly by using none. And where would you need to expand? You would need to expand here, the first column. The first axis, So that needs to be 1 by 3 by 2. 1 by 3 by 2 plus 2 by 3 by 2 would work, right? Just like A plus C worked. Exactly, A plus B, none. That would be correct, yes. 네, 윤재성님 말씀 맞습니다. All right, so this is all the concepts. Well, NumPy is such a vast library, so there's a lot of tricks and a lot of APIs that you can use to manipulate your objects as much as you want, as many times as you want. But these are the important concepts. So we went through the definitions, defining in different manners, like using ones and zeros and randoms and arrange, and then slicing and indexing. I'm not sure how to collapse this again. Oh, that's good. Yeah, slicing and indexing, math operations, shape manipulations, broadcasting. We covered all those. So those are all important concepts. Tensors, right? So 1, 2, 5, right? So yeah, we've covered a lot of things today, and we've done it in such a hurried manner because I only have 1.5 hours to cover this up, cover this entire content. So we did this in a bit of a hurried manner, but you need to really understand and get completely familiar with all these manipulation tricks, so that you no longer have to always refer to NumPy API search engines and every single time you define a matrix or whatever you want, and the practice sessions moving forward, starting from next Thursday and then the week after that, we will no longer explain all these simple manipulation tricks, like why we're doing this and why we're concatenating, how we're concatenating, when we're indexing, how we're indexing. We're not going to explain those anymore. Like all the basic explanations are done today, and then everything will be a bit more higher level starting next week. So please really get familiar with these concepts. And good way to do it is actually solving this quiz. So we don't have a lot of time today, so we only have 1 minute to go actually. So no time for you to do this now, but please do it on your own time. Actually, just go review all the things that we've done today, and then hopefully you can solve this quiz on your own. I can actually give you, when I upload the video today, I can actually update the class and post so that I can give you the answer to to this quiz, the answer would be like 1.011 something, if I remember correctly. So I'll post the answer to this quiz on Classroom so that you can check if you've done this correctly. So please do this on your own time. Get familiar, and then starting next week, we'll be moving directly onto PyTorch, and PyTorch has almost the same syntax as NumPy as far as matrix manipulation goes. All right, so any question before we end the class today? 질문 있으실까요? 제가 영어로 잔뜩 떠들었듯이 이거가 이제 완벽은 아니지만 충분히 이제 이게 익숙해지셔야지 앞으로 우리가 할 것들을 다 따라오실 수가 있어요. 앞으로는 우리가 뭐 인덱싱 할 때마다, 슬라이싱 할 때마다 이거 뭐 하는 거다, 왜 하는 거다 설명 안 할 거거든요. 앞으로는 계속 하이 레벨로 그냥 이제 네트워크 뉴럴넷의 레이어 정의하고 모듈 정의하고 이런 걸 할 거기 때문에 그 안에서 이런 매트릭스 어떻게 돼 이런 건 이제 설명을 안 할 거래 가지고 이런 것들이 충분히 익숙해지셔야 됩니다. 그래서 이걸 한번 다 복습을 하시고 퀴즈까지 푸시고 퀴즈 정답을 제가 올려드릴 테니까 클래스홈에 한번 맞춰보세요. Also, one important point is using 3 dots in indexing. 3 dots. Oh, actually, that is a good point. I haven't used 3 dots very often in my days because I was using Fiano in my grad school days. So, if you're familiar with 3 dots operation, you can actually post them in Classroom. Share your knowledge with your fellow students. Anybody can post things on Classroom, so please do. If you have some interesting information to share, I can even learn from you guys, so please do. Any other questions? All right, I'm gonna wait 5 seconds before we end the class. Okay, another question. Would a RTX 2070 Super be enough for local use instead of Google Lab? I would say so. 2070 has how many gigabytes of RAM? Is it 8 gigabytes of RAM? If 6. For projects purposes, I'm not sure if 6 would be completely sufficient, but I think you can still run it with a smaller batch size. Yeah, 8. Yeah, I think 8 is correct. So 8 would be probably okay. Yeah. I mean, all the projects that we do are relatively small sized. It uses a small network. It uses just, like a ResNet or that kind of stuff, which is relatively small compared to like modern transformer-based models. So, and the project number 2 is translation, which also uses like six layer transformers, which is also a rather small size network. So it would fit pretty well within 8 gigabytes of VRAM. So I think that would be okay. All right, any other question? Yeah, it's already 12:03, so we're running out of time. We're actually going overboard, so I'm gonna end class today. If you have any question, please post them on Classroom. And Ahmed, if you will, please share your knowledge about the 3 dots operation on Classroom. And I'll see you guys next Tuesday. Okay, thank you. Bye-bye.
감사합니다.
네, 감사합니다.
감사합니다.
네, 감사합니다.